9.4 vectors. So what is a vector?
Speed plus direction.
Right, that's one form of a vector, is speed and direction. So really it's a quantity that has magnitude and direction. So some kind of rate associated with it or something like that, and telling you which way to go, right? So a quantity that has both magnitude and direction. All right, so it's customary to represent it as an arrow, okay? And the length represents the magnitude and the arrowhead indicates the direction. So the length of arrow equals magnitude. The arrowhead indicates direction. All right, first off, we're going to look at geometric vectors, and then we're going to do them algebraically, because geometric obviously is a physical appearance to it. You can't necessarily get a specific measurement out of it, but you can get an idea, right? So if I would have a geometric vector, is basically a directed line segment. So if I have some point, let's say P, and I want to get it to some point Q, I would indicate it with a line with the arrowhead pointed towards Q, right? Very simple. The magnitude is the distance from point to Q. So this can be called vector PQ like this, and you put a little arrow on top of the letters, or you can give the vector a specific name. A lot of times vectors are used as vector V, like that. If you see it in a textbook, the V would be in boldface, and so that would represent a vector. They won't put the arrowhead on top. It'll just show boldface letter is a vector. Obviously, I can't draw in boldface letters all the time, so that's why in script we put little arrow on the top. You don't have to put like a double arrow. That's just my shorthand notation. I just put the little endpoint on it like that. All right, how do you add vectors? It's a couple ways. All right, let's say I have vector V. Let's change colors to red. Vector V is equal to, I don't know, something that looks like this, perhaps. And vector W, let's put it in blue maybe. Maybe it looks like this, perhaps. If you want to add two vectors together, there's a couple of different methods. You can take vector V and at the end of vector V, attach vector W. So V plus W would be vector v like this. And then I attach vector w to the endpoint in the same direction. We don't move direction. We don't change length or anything like that. And now the sum of these is from beginning to end. Blue and red make purple, right? Let's just put this. Not even purple. There we go. So this is v plus w, beginning to end. So this works with more than two vectors too. You can add 3, 4, 5, 6, 7. You just keep connecting from the previous vector to its endpoint to the next, to the next, to the next. And where you begin and where you end is your final sum of all those vectors. So beginning to end. Is v plus w. Now there is another method called the parallelogram method. It only works with two vectors, so if you got 3 or more, you can't make a parallelogram out of it. Is attaching the two initial points together. So it has v and w like this instead. V went there, w went here, and now you make a parallelogram. And from now, the two initial points together to the opposite end of the parallelogram now is your vector v plus w. You get the same picture. You'll get the same length of a vector in the same direction. And again, that only works for two vectors. If you got 3 vectors, you're not gonna be able to make a parallelogram out of it, right? All right, you got a few different properties of vectors. Can I say v plus w is the same as w plus v? Let's see. So let's take w. I'll go back and get my blue. W was this. And add v to it, red. And we should get beginning to end or parallelogram method would give us that. That's the same direction and same length, right? So yes. So vector addition is commutative. So it doesn't matter which order you add vectors in. You get the same picture. I have a little bit better display of vectors using right here. So you can move vectors around anywhere in the plane. Does not matter. Their direction stays the same, their length stays the same, right? So let's just say this one was, I don't know, v and w. I'm adding these two together. The sum of these would be my purple. This. Right. If I would put this one to this one, that's not right. I did it. Yes, it's supposed to be like this. Endpoint. There we go. I would have to draw a parallelogram if I was doing it that way. All right, so if I do red plus blue gives me purple. If I do blue plus red, notice it still gives me purple. All right. We can add in another vector. Let's say if I throw in different vector. Let's see, I had this, where was it? Shape. Let's throw in 3 vectors. So let's do red, plus blue, plus green. End result would still say, let's just do this purple, but it would be beginning all the way to end like that. That would be your sum of those 3 vectors. Really easy, it's very visual. But when you start getting multiple vectors, like 5 and 6 and 7, you can still draw these out if they fit on your paper, right? Because they all have to be scaled down some kind of manner to be able to fit. Some of these vectors might represent some kind of force that we're going to be looking at. So yeah, we can draw them, but then we actually want to do some math with it and make it a little bit easier to actually do the calculations instead of just moving things around here and there and then taking a tape measure and measuring. Even any type of measurement is only as accurate as the next person who comes and measures it and become even more accurate and becomes more accurate, right? So any measurement, you can be as more accurate as possible than the previous person. All right, so let's look at vector subtraction now. Difference of 2 vectors. So vector v minus vector w. You have to look at this as vector addition. This is vector v plus a negative vector w. So if w went this way, let me redraw my pictures again. Vector v, I don't remember exactly what they were, let's say that. And w was something like this. Well, what is negative w? Opposite direction, right? Same length though. So here is negative w. So now I just do the exact same thing I did before, attach to the first one's endpoint. Vector v minus w gives the result of this. All right, multiplying vectors by a scalar. This scalar is also a real number. All this does is change the length of the vector. Directions is still the same. It's just now the length. So if I say vector v is equal to, let's just say that, 3 times vector v is equal to 1, 2, 3 times as long. This is one of the easiest sections, I can tell you. Vector addition and subtraction and all that stuff. It's very, very simple. Once we start doing them algebraically, you can see how easy it is to. Really easy. Yeah.
I forgot this from last year, but do we ever put it on polar coordinates?
No.
No, you just leave it on a rectangular grid.
Yeah. Yeah. Some of the calculations we're going to do, you're going to see, are similar to the formulas we've done with polar equations and polar coordinates. All right, so magnitude of a vector, such as this. Let's say of a vector, let's say vector v. Is denoted as two double bars, almost like absolute value. And we saw magnitude earlier before, right? That was with in polar coordinates, right? We used r. R was the distance between this point at the pole to the point, right? That was also denomination magnitude. That's the distance, right? So it's the length of the vector. Component form of a vector. This is like ordered pairs. The initial point is at the origin. And the terminal point at the xy coordinate. But the component form looks like this. You don't use parentheses. You don't use brackets. You use like, what do you call those things? It's not really a less than or greater than symbols. I guess you could use those if you're typing, but it's 20 parentheses. That's what I'll call it, I guess, huh?
Angle symbol,
What?
angle symbol.
Angle symbols, yeah, angles, yeah. All right, so if I would say vector v is example 5, 3, this means I can put this like this, 5 units over to the right, 3 units up, and then draw from the initial point to the terminal point. That is vector v. And we call this vector v a position vector. The 5 and the 3 are the components, just like a and b, x and y are the coordinates. Yeah.
You're going to change the initial point, like to something else?
Yes, that's next. Yeah.
It'd be too easy if we did it right.
Yeah, yeah. Of course, that is the next thing. So, example. You should come teach this. You know exactly what's coming up.
No, I don't. I was just blowing.
I can take a break. I can sit back and just watch. Yeah, you can do
You
it.
know, I got you.
All right, suppose vector v has initial point Let's find my point. -1, comma 2, and terminal point, 4, comma 6. What is the position vector v? As its component form a comma b. Now you can memorize formulas if you want. This is not necessary. If you just think you need that initial point to get back to the origin, that's all you're doing. You can draw pictures if you need to help visualize it. We'll start off with that. So -1, 2, -1 up 2, that's your initial point. We're going to 4, comma 6. That's your terminal point. So we want to slide this vector down 2 units and 1 unit to the right, correct? So all you're gonna do is now, if I'm gonna slide it down 2 and 1 to the right, that means I subtract, right? 2 from the y, right? So I would have my terminal point 4, comma 6, subtract 2, that goes down, and I want to go right, plus 1. We now have this as the ordered pair 5, comma 4, which as the vector v is 5, 4.
So theoretically, you could think of it as taking the initial point and basically inverting the symbol and then adding that to the terminal point. Like if it's negative, make it positive.
You're just subtracting the values. That's all you're doing. 6 minus the 2, 4. 4 minus the -1, 4 plus 1, 5. That's all you're doing is subtracting. But this way you don't even have to think about, okay, especially when you start dealing with negatives and making an error right there. Then you're memorizing a formula in a sense, right? Subtracting the 2 points. Easy to make an error. Just you can quickly plot this, and you know this terminal point needs to move down to how this initial point needs to get to the origin. Down 2, 1 to the right. Subtract 2, add 1. And if you plot this, you'll see you have the same exact picture just now. 1, 2, 3, 4, 5, 1, 2, 3, 4, right there. There's your vector in position, your position vector now.
And what section was that?
This is 9-4. We're still in there. I just accidentally hit a button. All right, the unit vector. We can call it vector u. The magnitude of vector u would be equal to 1. So a lot of times we can take a vector and scale it down. And so we take any vector and actually make it in terms of A and B to where the length of that vector is always 1. So if I have along the positive x-axis, one unit out is this. You can call this vector I. And if I'm along the positive y-axis, one unit out, I'm going to call that one vector j. Vector I and vector j. So if I wanted to represent vector I in its component form, the coordinates or components would be 1 unit to the right, 0 up, right? Vector j would have component form of components 0 left or right, 1 up, so 0, 1. So any vector now can be written in terms of I and j. So vector AB can be also written as the A component times 1 comma 0. That tells you now I'm extending it by magnitude to go in the horizontal direction, and then also now plus B in the vertical direction, which is 0 comma 1. Those are I and J, right? So this is A times vector I plus B times vector J. So that's just another format. Makes things easier sometimes to work with. You get it out of its component form, and now you're in a, in a sense, polynomial looking format, like 5x plus 7y, something like that, right? Hey, this is algebra now. Very simple, combining like terms to add and subtract vectors. So the algebraic method, doing it this way, is really easy. So if I have, say, vector v has components 5 comma 4, this is the same thing as 5 times vector I plus 4 times vector j. So adding and subtracting vectors, subtracting algebraically. All right, so vector v plus w. Adding them's not too bad. It's subtracting them where you can have a little bit of careless errors. But if you put them in this AI plus bj format, you have this is 2i plus 3j, right? Added to 3i minus 4j. You're just combining like terms. Gives you a total of 5 i's. Negative, and 3j's plus a negative 4j is negative 1j. So if I wanted it back in this component form, I can rewrite it back as 5 negative 1. So you could have looked at that without having to transform them as well. Add the A components, 2 and 3, gives you 5. Add the B components, 3 and negative 4. That gives you a negative 1. Right? So the addition part's easy. If I would say, let's do W minus V, this is where I think it makes it a little bit easier to keep track of. You obviously can make a careless error trying to subtracting negatives a lot, doing all that in your head. So if you put it in this AI plus BJ format, we have 3i minus 4j minus all of v. So that's why I got to put parentheses of 2i plus 3j. And if you got parentheses, minus parentheses, you got to distribute across to get rid of the parentheses. So that'll be 3i minus 2i is 1i. Negative 4j and negative 3j is negative 7j. Or if I want it back in component form, I could do that. That's going to be 1 comma negative 7. You can still always do these algebraically too. I mean geometrically. Plot these and then see where the result would be. Now, it might be hard to actually see if you're not using graph paper and really being really accurate, right? Doesn't necessarily say that you're going to be exactly at the point 1 comma negative 7, right? You might look at it and say, it looks like it's 6.8. Got to be really accurate, right? So that's why the algebra gives you the exact answers. You can't necessarily get those from a graph. All right, what if I would do something like this? Same vectors, let's do 2v minus 3w. Still, this is just algebra. 2 times vector v is 2i plus 3j. Minus 3 times vector w, 3i minus 4j. Distribute, combine like terms. 4i plus 6j minus 9i plus 12j. That's negative 5i, and that's plus 18j. What is the magnitude of v? So I want to know how long is that? That's the length. V is 2i plus 3j, right? So 2 comma 3. How will I find that? I know the formula.
A squared plus b squared equals c.
Yeah, it's Pythagorean theorem. So the magnitude of that is the diagonal, the hypotenuse of the right triangle, right? So this is nothing more than the square root of a squared plus b squared. You can use x's and y's if you want, it doesn't matter. Just most typically vectors use components as a comma b, right? It's the same numbers we would have here. This is the square root of 3 squared plus 4 squared. That's 9, that's 16, that's square root of 25, which is 5. What is the magnitude of vector v plus w? Be careful with this. I'm not going to take each magnitudes and add them together. I'm going to take the sum of the two vectors and then find its magnitude, right? It's kind of like a grouping symbol. What you do inside comes first. V plus w, we already did that one. V plus w is 5i minus j, right? Or 5 negative 1. So the magnitude of v plus w is the square root of 5 squared plus negative 1 all squared, which is the square root of 26. All right, let's find a unit vector. All right, so we know that the unit vector, its magnitude is equal to 1, right? And the unit vector u has the same direction as a given vector v. We're just taking this vector v and shrinking it down. That's all we're doing. So the unit vector is nothing more than a vector v divided by the magnitude of that vector v. Because look, if you multiply this, the vector v multiplied by the unit vector is equal to the vector v, right? That's what we just said. So if I go backwards, you see that unit vector is the vector v divided by its magnitude. So if vector v is equal to, say, 4i minus 3j, what is the unit vector for vector v? Very simple. Find the magnitude. Square root of 4 squared plus 3 squared. We just did that, really. That's square root of 25, that's 5, right? So the unit vector, sometimes they put a little v underneath, like this is a subscript to show that it's related to the vector v. Sometimes they don't, but we're just going to leave it like this. Is equal to the vector v, rewrite what it is, 4i minus 3j, all over the magnitude 5. I split this up into two fractions where they have a coefficients in front of I and j, 4/5 I minus 3/5 j. If I put it in this component form, I could do that as 4/5 and negative 3/5. So either one is acceptable. I'm just saying however far you want to go. If you want it in its component form or leave it as a I plus bj form, that's fine as well. But that's as very simple. So if you would take this and you can see, okay, what defines it to be a unit vector has a length of 1, right? This is the x coordinate, or a. This is the y coordinate, or b. A squared plus b squared. If you would do this, you get 16 25ths plus 9 25ths is equal to 25 25ths, which is 1. Square root of 1, 1. Length of 1, right? Has a unit length of 1. So you're just shrinking this down. That's all you're doing. Scaling it down. Still easy, right? Speak now, forever hold your peace. Right? Any questions though? There's like, am I moving too fast? You need to slow down. Most of you have probably seen a lot of this already if you've taken some kind of like probably physics in high school. This is very simple physics. All right, let's look at remember the unit circle? Yeah. Let's see how good I could draw this picture. Actually, I should have did it this way first.
I'm into this.
That looks like an oval.
That's the circle. I draw perfect circles.
Well, I use software. The software is supposed to-
I can't draw straight lines though. There we go. I don't like that one. That's pretty close. All right, I'm only concerned actually with quadrant 1, so I'm gonna just go ahead and erase everything I've drawn over here. There's no quadrant 1 is a reference to everything else, right? So I'm not going around and doing the unit circle stuff. In fact, I'm not even gonna put like those special angles that we know of on the unit circle. Those aren't important to us right now. But on the unit circle, I have some angle going like this. And from here to here is length of 1, right? This is a unit vector right here. If I'm on the unit circle, my x and y coordinates are represented as a cosine of some angle. Let's call this angle, I guess, alpha, comma, the sine of alpha. So this would be alpha right here, right? Remember, those coordinates like that only appear on the unit circle because cosine is x over r. Remember that from trig? In this case, r is 1, so that's why it's just simplified to just cosine. Sine, same thing, all over r. So if your hypotenuse is 1, this makes it really nice, right? All right, so this is 1 unit here, this is 1 unit there. This is the which vector going in this direction. 1 unit out. That's the I vector, right? And this would be the J vector. This is my vector V, however long it is. We said any vector can be rewritten in terms of I and J, right? So the unit vector right here has components A comma B. You want to think of it that way as well, where they're the same as the points cosine, sine, right? So my unit vector can be written in terms of I and j as the cosine of alpha times the vector I plus the sine of alpha times vector j. Just like we had AI plus bj, right? This is A. And this is B. But we know if the unit vector is equal to the vector v divided by the magnitude of vector v, right? Let's put those in this place. If I cross multiply here, I have vector v is equal to the magnitude of vector v times the unit vector. So vector v is equal to the magnitude of vector v times the unit vector, but the unit vector is this. So this is another way to express a vector, given its magnitude and its direction. Magnitude, direction. Yeah,
You said we weren't gonna put it on a polar graph. That's
not polar.
Oh, wait. Yeah.
It's similar.
It's similar.
It's similar because polar uses cosines and sines and all those things like that to figure it out. But it's the same, everything's meshed on top of each other, rectangular system, the solar system, the complex system. Now we got vectors, all using the same things. It's basic free, right? Right triangle trigonometry. Yeah. All right, throw a ball with an initial speed of 25 miles per hour. We don't know the angle it's being thrown at, perhaps. We might see that in a second. But you could throw that ball nearly straight up. You can almost throw it nearly horizontal, right? But it's going to take on some kind of path, right? So let's just say as you throw this ball with initial speed of 25 miles per hour in a direction that makes an angle of 30 degrees with the ground. Express the velocity. Let's call it V in terms of I and J. You can draw a picture if you wish, this doesn't matter. 30 degrees. The magnitude. Remember, a vector is magnitude and direction. We've got the direction. What's the magnitude? 25. Speed with direction is velocity, right? So we know the format, vector v is going to be the magnitude, which is 25, times the direction is in the form of i's and j's, right? So that's going to be the cosine of 30 degrees times vector I plus the sine of 30 degrees times vector j. simplify this. What's the cosine of 30 degrees? No, or 3/2. Here's the other one. Yeah. On the test, don't guess. Put it in a calculator to make sure, right? Sine of 30 is 1/2. Distribute the 25 across, and then you have it totally just as I and j. That's two terms. 25 square root of 3/2 times vector I plus 25 halves vector j. So if you want to look at it as individual horizontal vectors and vertical vectors, the x, the horizontal, the y, or the a and the b, if you want to think of it that way. This is your horizontal component. This vector added to this vector makes the diagonal component, right? So this is your vertical component. So the sum of those two vectors gives you the diagonal of 25 miles per hour. So if you want to actually see how much were the initial speed just horizontally and how much initial speed is vertically, there are your two values right there. This is just 25 square root of 3/2. I have that put in the calculator. That comes out to be about 21.65 miles per hour in the horizontal direction. And then 25 divided by 2 is 12.5. Vertical direction. You don't see these, right? The ball is traveling on the diagonal. But that's the two components that are forming that 25 miles an hour at the 30 degrees. Questions? Good to go. All right. Flying run 737. But how fast you think you're going? Really fast. When you look out the window, you don't even realize you're going that fast, right? Flying, you just look like flitting along. You're doing about 500 miles an hour. You don't realize it. So let's just say this plane is at a constant speed of 500 miles per hour, heading due south. So what's due south of here? Cancun? I don't know, somewhere. Right? That sounds like a good destination.
Puerto Rico.
No, that's not due south of here. It's more east. southeast, but not too south.
In Mexico.
You're going to Mexico somewhere, I guess, right? All right, the jet stream is 80 miles per hour. Northwesterly. Express the velocity. Let's call it VA. Of the 737 relative to the air. And velocity V sub W of the jet stream wind. In terms of I and J. So just very similar to what we just did earlier. I want to express it with their magnitude and their directions. So we can draw a picture. Yeah.
Why do you have to put the whatever the weird triangle is over V sub A and V sub W? Because so technically,
This,
yes.
yeah, I just forgot. Just pain. Try to draw those all the time. I wrote them in boldface. How about that? All right, so 500 miles an hour heading due south. Jet stream is 80 miles per hour northwesterly. So let's draw a little picture of this. Easiest way to put it in the XY coordinate system. All right, due south. Starting from here, straight down, right? So this is VA. The other vector, the jet stream, is traveling in a northeasterly direction. So northeast is like that, right? And that's 80, right? So this is 500 in magnitude. This is 80. Like that. So from this picture, let me zoom in on it. We need to figure out their angles. I have their magnitudes, I just need their directions. How far is it from here to here? If it's exactly northeast. 45, right? So let's say this is alpha is 45 degrees. And then from here all the way to here, how many degrees is that? We can do degrees or radians, but let's stick in degrees, make it easier on ourselves. Huh? A quadrantal. 270. Let's call that one beta, I guess.
Okay.
All right, so VA. Let's work on that one, I guess, first. Its magnitude is 500 times its direction is by the cosine of that angle. That angle is 270 times vector I plus the sine of 270 degrees times vector J. Cosine of 270 Think about unit circle. The order pairs from the unit circle. Cosine is the x coordinate. To get down there, that is 0. How do you get down there? Sine would be -1, right? So this is just distribute across, that's 0, that's negative j in the parentheses, 500 times negative j, negative 500 j. Does that make sense? You didn't even have to do the arithmetic. Just look at it. You're on the j vector, the opposite j vector, right? J vector goes up, negative j vector goes down. 500 times that is the magnitude, right? So this is VA. V sub W. Do the same thing we just did. Magnitude is 80. The cosine of the 45 degrees times vector I plus the sine of 45 degrees times vector J. Evaluate those. Sine and cosine of 45 is both. Yep, square root of 2 over 2. Distribute across, simplify. That gives you 40 square root of 2 times vector I plus 40 square roots of 2 vector J. All right, so I don't know how much flying y'all have done before. Ground speed and air speed are two different things sometimes, right? Wind affects how fast the plane goes, right? So just think about it. If you're on the runway, you're not flying at all, you're on the ground. But you got a 20-degree wind, 20-mile-an-hour wind coming straight at you. The plane's air instruments are going to say that you're doing 20 miles per hour. That's airspeed, right? You're not moving anywhere on the ground at all, but the plane kind of thinks it's flying, right? So what if I ask you, what is the ground speed with this scenario? So what, this is part B, find the ground speed. Of the airplane. So this is actually, let's call it VG. The airspeed indicator is saying that you're doing 500 miles an hour, but you got this 80-mile-an-hour wind pushing you some direction. Are you really doing 500 miles an hour on the ground? No, probably doing slower, right? So let's see. All I have to do is the ground speed. Actually, this could be the magnitude, right? Magnitude is, I don't want the entire direction. I can find the direction in a minute, but I'm looking for just the ground speed. So I'm looking for the magnitude of G, which is the magnitude of the sum of those two vectors we just found. So if I add those two vectors, VA was negative 500J. Plus VW, that was ugly, 40 square root of 2 times vector I plus 40 square root of 2 vector j. So I'm still looking for the magnitude. Add these two together. That's going to be 40 squares of 2 vector j minus 500. Let's just write it like that. Let's put the I first. 40 square root of 2i plus 40 square root of 2 minus 500 times vector j, right? So the magnitude of that is just nothing more than the square root of the a squared plus the b part, 40 square root of 2 minus 500 squared. Of course, I'm missing a page in my notes. Let's see. These notes are so old, it's time to rewrite them.
You change the sign order to the letter I up on the second step.
Oh, that should not be a negative, right? I don't know why I did that. But either way, it's squared and positive.
Yeah,
So, but that's you correct, though. All right, so let's plug all this in. See if my mouse will cooperate with me. Which is not. Let's bring up the calculator. All right, so 40 square root of 2. I square that number.
30,000.
Yeah, 3,200. I'm gonna write that out first, I guess. And 40 square root of 2 minus 500. Squaring that. This big ugly number 2. Add 3,200 to that. And then take the square root. 447. So you're really doing about 447 miles an hour tracked on the ground. That's how you can actually tell how long it's actually going to take you to get to your destination, right? What is the actual track on the ground? So this is C. So you think about it, if you take off and looking at your compass heading and it says I'm doing due south, that wind is pushing me, right? Eventually eastward. So eventually by the time I get to my destination, I am no longer due south of my original destination, right? So if you know the wind speed and the direction it's coming from, that's where you got to compensate. So that eventually, over time, you can end back directly due south of your location. All right, so we've got this vector influencing this vector, right? So we know it's going to get pushed that direction. So the sum of those two vectors, again, is going to give us our picture. So you can make a parallelogram if you wish. We're going to be tracking something like that. So I need to find a direction angle for this. So how would I find a direction angle? All right, VA plus VW, its final AI plus BJ format was the negative 500. Actually, the 40 square root of 2 first. Times vector I plus the 40 square root of 2 minus 500 times vector J. think polar coordinates, complex plane, those kinds of things too. How do we find the angles? R was always found by the Pythagorean theorem, right? Same thing. The angles are always found the same way. Inverse tangent, B over A. And whatever our calculator is going to tell us, we may have to make a slight adjustment, right? To give us the angle that makes sense to us. We know we're going to be in quadrant 4, right? Just logically that happens. I mean, that has to happen. We're going directly due south, we're getting pushed over to the right. It has to be quadrant 4. So if I put this in the calculator, inverse tangent of the B is the part in front of the J, AI plus BJ. 1, too many zeros. 40 square root of 2 minus 500 over 40 square roots of 2 would equal our angle, I'll call it theta. Yep.
Before, actually, no, it's not that quite inclined.
So inverse tangent, parentheses, 40 square root of 2 minus 500. That's the numerator divided by the denominator of 40 square root of 2. And then we get a, oh, I'm in radian. Let's put it in degrees. So negative 82.7. In the real world, would that make sense to go around and say, I'm going negative 82.7 degrees? From what? Well, that's this direction. I mean, yeah, remember bearings and those kinds of things? Okay, so if you just give the angle, you have to say from due north. Okay, so from due north, being 0 degrees. This is 90 to here and 82.7 there. This is equal to 172.7 degrees. That's your heading. On a compass, due north is represented as 0 degrees, due south is 180, due west is 270, due east is 90 degrees. So it doesn't follow the right XY coordinate system and standard position of angles. Go figure. So if you ever at the airport, every runway has numbers on it, right? If you ever want to know which direction you're taking off into, if I say I'm over here, think about it, I'm going due south. Gotta kind of look upside down, turn your head upside down. You'll see runway 18. Add a 0 to that. 180. You're going due south. 180 is due south. On the opposite end, 180 degrees more than 180 is 360. You'll see runway 36. You're going due north if you're going that way. And if you got east-west runways, this will be taking off to the west is runway 27. Taking off to the right, due east is runway 9. Just add a 0, as I always tells you. Not all runways are exactly those, but that's the most common runways that you see those numbers. And some of them are diagonal. It all depends where the majority of the winds are coming from in that direction all the time in your location. So they'll build the runway in that direction. Planes always take off into the wind as well. Because like I told you earlier, if you're sitting on the runway, and there's 20-mile-an-hour wind, the plane is already flying at 20 miles an hour. The wind is traveling over the wings to already give it lift. I used to plow, so that's why I know some of that stuff.
What's your flight for?
Myself, student pilot. Well, I had a private pilot's license, but I have not flown in years and years, so it's kind of expired. And it's a really expensive hobby, so extreme.
Fueling up.
Yeah.
Especially now.
Yes. All right, so that is 9.4. Any questions?
Good class today, sir.
Good class today. It's over.
You stopping the recording?
And I just didn't have a video for 9.4, so I had to record this one.